Hi, I'm Won Lee. I introduced the random variable yesterday. It is key tool in statistics. And I'm going to explain classification of random variable x and definition of f of x today. Okay, let's see. Classification of random variable x and its corresponding probability distribution definition. Okay, from now on, we refer to population as a random variable x. What is x? X is the like function, sample space to real number, say population. Okay? Statistics theory is developed concerning the population. It is essential to understand the probability distribution of random variable x, f of x. Let's go back to this diagram here. X, random variable x, play like function, sample space to real numbers. This is a population. There is probability on sample space. There is probability distribution function, f of x, on population. Okay? Go back to today's classification of x. X can be classified into discrete and continuous types. When x takes a countable values, countable with fingers, okay, then it is discrete type. The other cases, otherwise, it is left as continuous. Let's see some example. Okay, face numbers of a die: 1, 2, 3, 4, 5, 6. How many? 6 many. Countable. Okay, this is a discrete type of a random variable. Satisfaction level on a 5-point scale in a survey. You get a data, dissatisfied, neutral satisfied, very satisfied. So assign number, real number here: 1, 2, 3, 4, 5. This, of course, is discrete type of data. Third, scores 100 multiple choice exam question, 100 questions. Then scores 0, 1, 2, 3, 4, up to 100. There are what? How many? 101 many value here. So we can say it is discrete, but actually it is appropriate to consider as continuous. Okay, scores is continuous type of a random variable. Okay, for car speed, temperature, height, fees, etc. There are many continuous variables, continuous type of random variables. Okay, you get it? We will see this type of data later. Let's express probability distribution function, random variable x, as f over x, whether x is discrete or continuous. Okay, sometimes some textbook distinguish the name of the probability distribution function f of x when discrete probability mass function, when continuous probability density function, like that, but it is no use. Okay, we have a population. Population means random variable x. Random variable, if you have a random variable, you have a population, then it will have some probability distribution function, f of x, like this. Okay? And another thing, random variable should be denoted by capital letter x. You have to distinguish small letter x. Small letter x is some specific value. I will explain it later again. Since we do not know the value of the population, we do not know all the data of a population. So the distribution is not known too. We don't know the data in population, so we do not know the distribution, probability distribution. Okay, so we have to make an assumption population or X has some specific probability distribution function f of x. F of x is not known. Understand it? Okay. Here is definition of a probability distribution function f of x. Random variable x follows a certain probability distribution f of x. Can be also said x has a probability distribution f of x. Okay. In this case, f of x must satisfy the following condition. 1. F of x greater than equal to 0 for all x. Because it is a sort of a probability, so cannot have a negative value. Okay? Greater than equal to 0. For discrete case, because it is countable, sum of f of x equal to 1.0. For continuous random variable, instead of summation, integral notation. Integration means the area under the curve. Integration give us the area under the curve like that. Okay, but integration is not easy, so that I will not talk about integration in this lecture. Okay, we only deal with summation, discrete case. You may see integration notation later, but you don't have to understand or follow. Okay, what is the difference between discrete and the continuous random variable? What is the difference? We have already obtained the histogram using 82 work processing times in earlier lecture. Okay, 82 numbers, integers. Okay, we may consider this data as a population data. Population is 82 numbers. Let's compare the graph when these 82 integer values are treated as discrete data, left-hand side here. I already explained that actually, versus when treated as continuous data, right-hand side. Although the data is composed of integers and may be considered as discrete, right? Countable. This is 82 numbers, countable numbers. Time is countable numbers. The unit is minute. So 22 minute, 22 minute, 20 minute, something like that. It is reasonable to treat it as continuous. When you consider this as discrete, when treated as discrete, the sum of heights of the probability, this is a probability on what? Sample space. So sum of heights maybe should be 1.0. Okay? Here, 100%. Relative frequency. But when you consider this as continuous, then you have to know the area. When treated as continuous, the sum of the areas of the bar is 1.0. That's why I emphasized at the time, I think lecture number 4, the sum of this integration of this curve. This maybe say as like this curve. So when you have discrete case, then sum. When you have continuous case, you need to get areas under the curve. Okay? I hope you understand this one easily. Okay. Thank you. Bye.